Yeah, is my screen clearly visible?
Yes, sir.
Yes, sir.
So today we'll be covering the contents of week 2. The contents of week 2 will be covered over 2 sessions. So this is session 1, and on Thursday I'll cover the remainder of the topics. So the plan is to cover determinants, Cramer's rule, and inverse of a matrix. Let's call it square matrix. So already you guys have seen in week 1 that how to compute determinants, right? So suppose I'm given a 3x3 matrix. First of all, determinant is something that can be computed only for square matrices. It's a number associated to this matrix. Let's take the simplest case first. The matrix given by A, B, C, D. So what is the determinant of this?
AD minus BC.
The AD minus BC.
Yeah. Now if there is a 3x3 matrix, let's put some numbers over here. How would you go about computing the determinant? You don't need to go through the computations. Just if someone can tell me what is the procedure, that will also be fine.
So 1 into 5.
Determinant of 5, 6, 8 and 9 minus 2 into determinants of 4, 6, 7 and 9 plus 3 into determinant of 4, 5, 7 and 8.
Yeah, there's a determinant over here. And 3 times determinant of 4, 5, 7. So more generally, if I have, and this we can continue and take it to its finish the computation. But more generally, if I have A11, A12, A13, A21, A22, A23, A31, A32, A33, then the determinant of A is computed using the formula summation j going from 1 to 3. Let's call it minus 1 to the 1 plus j A1j and what is it called? MIJ, I believe, M1j. This is a formula that has been covered in week 1,
Yes, sir.
and everyone understands what this summation is.
Yeah.
It's just you take A11 and multiply it by the determinant of the matrix that remains after you. Is there a doubt?
No, sir.
Okay. So you take A11 multiplied by the determinant of the matrix that remains after you remove the first one, the first column, then minus. So there's an alternating sign as well. But over here, this expression for the determinant involves what can be described as taking the determinant along the first row. There's nothing special about the first row. We could fix any row and take this. Has this property also been covered?
Yes, sir.
So this property is also being covered, but in a different manner. I plus j minus 1 power I plus j, where I denotes the number of rows and j is the number of column. Suppose I value of I is 1 and j is also 1, then it denotes the first row. Then minus 1 will become 1. That's in this process they taught.
Right, yeah. You have to fix one of the things. So the most general formula is determinant of A is equal to, suppose I'm expanding along the ith row, it will be or just to emphasize that that coordinate is fixed, I'll just write it as I naught row. Then it would be I naught j. You have three terms over here, right? A,
Yes,
you
sir.
are going to multiply A I naught 1 with M I naught 1 with the corresponding sign. And you do this for all j. So you can fix any I naught, and this will be the determinant.
Sir, but here we have to define na I comma j equal to 1 to 3.
No, then you will be taking 9 elements. No, that will, it's not I comma j. You have to either fix I or fix j, because you are taking it along either a row or a column. You cannot vary both rows and columns.
Oh, here you are not defining entire determinant of a matrix.
This is the determinant of a matrix. So, for example, the determinant of, let's go back to this itself, right? Let's go back to this itself. Suppose I'm expanding along
Hmm.
the second row.
Hmm.
That would be, first of all, you write it as A21 determinant of, let me just call it M21. Now I'll not uh, explicitly write that down. A22, M22, M22 being the determinant of the matrix obtained by removing second row and second column, plus A23, M23, correct? So
A
you see
3
this is fixed.
means 5. A23 value is 5. Uh,
A23 is 6.
oh, 6, 6, sorry. 6.
Yeah. So when you are taking it along this row, this is the expression, correct? So you see that A21, A22, A23, all these things come
Oh,
from the same I.
oh, you are fixing a row.
You have to
Uh,
fix a row. You
Oh,
cannot you cannot do over I and j. You cannot sum over I and j. Then you'll get 9 terms. That is not the definition of determinant.
So we can fix any row and any column, right? So we
You
have
can
the
fix any row and any column. That is what I'm trying to emphasize over here. That this I naught could be anything, but it has to be fixed.
okay.
What is the M 21, M 22?
Minor. It's minor.
Okay, so let's see in the case of this specific 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix. Just a moment. So when you say A21, M21, correct? A21, this is A21. This 4 is A21. So what should A21 be multiplied with? It has to be multiplied with M21. What is M21? You take A21, ignore the column and row that it corresponds to. And what are the numbers that are left? 2, 3, 8, 9, right? The determinant of that submatrix 2, 3, 8, 9, that is called M21. Similarly,
Can
now
I
if I
explain you
do,
once again? M 20.
okay, sure. So what have we done over here? We have done 1 times determinant of 5, 6, 8, 9. So how did you get that term 1 into determinant of 5, 6, 8, 9? You looked at 1, you looked at you deleted the row and the column corresponding to 1. And what is left? 5, 6, 8, 9, correct? In this matrix, if I remove the column and row corresponding to A11, which is 1 in this case, what I'm left with is a 2 cross 2 submatrix, which is 5, 6, 8, 9. The determinant of that is actually called the minor, which is denoted by M11. In this case, it is actually 5, 6, 8, 9. Maybe if this is not clear, let's do this example more explicitly.
Sir, one question. Why is that called M21? I mean, I'm trying to understand. I understand the minor part, 5, 6, 8,
It is
9.
called the minor of a minor corresponding to the index 2, 1. So this is different. So wait, these two things are different. Okay. So maybe this is causing confusion, as in the final result will be the same. Determinant. So this is A11. This is M11. M11 is the minor, which is or determinant of the submatrix obtained by deleting the first row and the first column. That is 1, 1. One row and one column.
Yes.
Minus, if you have A12, M12, this is the determinant of the matrix, which is obtained by removing the first row and the second column.
Yes, I
That is
got
why it
that.
is M12.
Yeah.
And then you have A13, M13.
M13.
M13 is the determinant of the submatrix obtained by deleting first row and third column. Row number 1, column number 3. If you do
Yes.
that, you'll get M13.
Yeah, I understand this now. Only thing I wasn't understanding the previous where you had put M21 there, and that part I did not get, but I think this one I get it.
But it's taken the second row.
So in general, Mij is determinant. Wait. Determinant of submatrix. I just write it as matrix. Matrix obtained by removing row I and column J. All right. So with this notation, you'll have A11 M11 minus A12 M12 plus A13 M13. So let us actually do the computation. This would be 1 times something like 45 minus 48 minus 2 times 36 minus, if I make any computational error, please let me know. 3 times 32 minus 35. This would be what? Minus 3. 36, 42, 6, 12. Minus 9. So this will be, this determinant is 0. Is that correct?
Yes.
Can determinant? Yeah, this is correct, I think.
Yes, it's correct.
Yeah. Determinant is 0. Now the second point I was trying to make is that for a general matrix, you can write this as the formula for the determinant. But there is nothing special about the first row, is what I was trying to say. Here, what you have done, you have taken the first row. I'm not going to write this A11, M11 thing again. But you have taken the first row, and for each element of the first row, you have computed the minor corresponding to that element and multiplied it along with an appropriate sign. All of that can be condensed into this equation. So it is the sum of A1j, M1j, along with the appropriate sign, which is given by -1 to the 1 plus j. And you are summing it across all the entries in that row. But this part says that there is nothing special about row number 1. You can take any row, call it I0, row number I0, and you sum it along only the columns corresponding to that row. You fix that row, you look at all of the elements, and then you compute the same thing. Instead of wherever you have 1 in the previous formula, you make it I0, and then this works. Of course, we'll see this in the example only, then this will be more clear. But as a final note, I'll just say that you can do this along any row as well. For this also, we'll work it out in this particular example, I plus j naught. If I fix a column and go along the rows of that column, that also works. Now, what does all of these mean? I'll in this thing we'll see again. So once again, A is 1, 2, 3, 4, 5, 6, 7, 8. Now, we know that determinant of A is 0. That we got by computing it along the first row using this formula. Now, what about second row? If the property states that it doesn't matter what row you choose or what column you choose, the determinant is, you can compute it that way as well. So if we are to do it, let's say along the third row, let us take third row and compute the determinant. It should not be different, but let's just verify. So over here, okay, when we're doing column, we'll probably do second one. So over here, the signs that you have to attach to the entries are given by -1 to the I plus j. This you can remember as this is plus, minus, plus, minus, plus, minus, and plus, minus, plus. All right. So if I'm doing it along the third row, how do I follow the procedure? I write it as 7 times determinant of
2, 3, 5, 6.
2, 3 minus 5, 3.
2, 3, 5, 6.
this is it. Yeah, if I do 7, I'll get 2, 3, 5, 6, correct? Let's do
Yes,
it quickly. 2, 3, 5, 6 is 12 minus 15.
Yeah.
Correct? And then you get a minus sign. Strictly speaking, I should be writing -1 to the power what 3 plus 1. Right? So this is this
Yes,
7 is a entry number 3, 1. So it is -1 to the 3 plus 1, which is plus. But 3 plus 2 will be minus, so I'll get a minus sign over here. 8 times determinant of
6 minus
1, 3, 4, 6.
Minus 24.
6 minus 12.
So that's 6 minus 12, right?
12.
Plus 9 times
5 minus
1,
8.
2, 4, 5. This is the
minus 8.
matrix that you're working with.
Yes, sir. 5 minus 8.
5 minus 8. So this becomes 7 times minus 3, which is minus 21,
Minus 21.
plus 8 times 6,
48.
and whatever is remaining. 9
Minus
3 is
27.
27.
And this is also 0. So this was expected, but where this will be useful, I'll give you an example later on.
Sir, quick question. How did
Yeah.
you get -8 there? I thought it will be +8, right? Out there.
So
The second term.
the factor that has to be the factor that contributes the sign is -1 to the power I plus j.
Correct. So 2 plus 3, right? So that is -1 to the power of 5 will be -1.
Yes, that's why you have a minus.
So, but then you also have to do minus, right?
No. It's
Actually, you
that
multiplied
sign
with
comes
minus
from
1.
Okay,
Always
I got it,
minus
I got
6,
it.
right? And when we multiply minus into minus, then it's plus.
No.
So
Actually, I got
when
a
you do
little.
summation
Yeah, I got a little.
I plus j. You got it? No?
Yeah, I got it. I was
Yeah, okay.
mapping it to the first row operation where it is plus.
Yeah,
minus.
the first row operation is a specific case of this formula.
Got it.
So yeah.
Yeah, I got
All
it.
right. So if we do it now along, let's say the second column, let's do it along the second column, just to make sure we understand what is.
The first row also follows this operation only, right? So
It follows the same operation.
okay.
But the property says that there's nothing special about the first row. You could do any row or any column. So
Okay.
let's just verify it for the second column as well. 2 times what would be remaining? 4, 6,
So
7,
there are no specific conditions, no, right? Which column or which row we have to consider?
There's nothing like that. It is only in certain cases you will find that working with certain rows may be easy. I'll give an example to demonstrate that as well.
The rows or column which have more zeros, it would be easy to calculate.
Yeah, of course. That is the
Or smaller numbers, the rows or columns that have smaller numbers, they'll be easy to calculate.
you cannot say what will happen to the corresponding minus, right? So as long as the rows have zeros, you can always guarantee that it will be 0 times something, so it is 0. So it's always better to work with one which has more zeros.
Okay.
Even then, it is like computation of determinant is not a thing that is complicated because you have programs to do it. This is just theoretically to get an idea of how to choose better initial conditions in general. So let's get back to doing computing the determinant along the second row. We'll have 2 times determinant of, now it will be 1, 3, 7, 9.
No, sir.
But here,
4, 6, 7, 9, sir.
Oh,
4, 6, 7, 9.
7, 9.
oh, right, sorry.
Yeah,
That's
4, 6,
4, 6, 7, 9. Yeah. And there's a minus sign over here on this time. And then you have plus 5 times determinant of 1, 3, 7, 9
Yes.
minus 8 times determinant of
1, 3, 4,
1,
6.
3,
3, 4,
4,
6.
6. Yeah. So here you see that sign convention, I mean, the sign convention is still followed. But the thing is, here you get a minus plus minus instead of the plus minus plus that you got in the other two cases, because this is the second term.
Why is it -2?
Why
Because
is the
you're
-2 is
operating on column 2, right? Or column 2 is 2, 2, 2, right? Sorry,
So
first row and column 2.
So this
Got it.
is
No, I'm good.
1, 2.
Thank you.
Yes, sir. Actually, I have also that same rule.
So it's always -1 to the I plus j. If you get confused, you just use -1 to the I plus j.
So there is 2
Or
plus 2, sir, right? It will be 4. It will be even.
that is this one. That is plus.
Yes, sir.
Yeah.
Okay,
And this
okay.
is
Yeah,
minus.
sure, sure. Correct, sir.
So I'm having doubt now. Hello?
Yes.
How do you got -2 plus 5 minus 8?
Once again, it's
Earlier-
always -1 to the I plus j. Okay. So here, what is this term? This term is A12. This term is A22. This is A3.
A32.
So here you have a -1 to the 1 plus 2. Here you have a -1 to the 2 plus 2. And here you have a -1 to the 3 plus 2. So this will get a minus sign, this will get a plus sign, this will get a minus sign.
So we can simply follow the odd even, right? Even it will be plus sign, odd will be negative sign.
So earlier format showing is a plus minus plus, and for example, +1 -2 -3 sign again +4 like that. No?
So this
That is a row format.
Even in the row or in the column, when you are expanding along a row or a column, you'll have this of the form Aij times Mij, right? Aij times its corresponding matrix. The sign that accompanies it is -1 to the power I plus j. That is the blanket rule. And in this case, what happened was, take for example, if I expand along third row, this was A31, which is accompanied with the sign -1 to the power 3 plus 1, which is plus. And then you have A32, which is accompanied with -1 to the 3 plus 2, which is a minus. And A33, which is -1 to the power 6, which is a plus. So in this case, it was plus minus plus. But in this case, what happened was this was A12, this is A22, and this is A32. And in this case, the sign that came along with this is -1 to the 1 plus 2. And in this case, it was -1 to the 2 plus 2. And in this case, it was -1 to the 3 plus 2. So this is a minus plus minus. So for a 3 cross 3 matrix, you can actually, that is what I was doing earlier. You can do this plus minus plus minus plus minus plus minus plus. So these are the signs that will accompany the corresponding entries. Of course, you will be using only 3 at a time in any computation. So if you expand along the first row, it will be plus minus plus. If you expand along the second row, it will be minus plus minus. If you expand along the third row, it will be plus minus plus, and so on. So whether it is plus minus plus or minus plus minus, you don't need to, memorize that. You can just remember that it is -1 to the I plus j.
Sir, I have a related question which has been bothering me for a while.
Yes.
Suppose you do a row operation on that matrix while finding the determinant. Say you do like R2 is equal to R2 plus R1 or something like that.
Okay.
In that case, is it necessary to use R2 to find the determinant because you have done a row operation on that particular row?
No, determinant is a number associated to a matrix, not using any row or any column. To prove that property, it's probably easier to expand along the changed row.
Right. So it's not necessary to expand along the changed row, right? You can still operate on any row. Okay.
Yes, you can still do that. Yeah.
Okay, got it. Thank you.
Yeah, let's just finish this computation quickly and move ahead. This will be minus 2 times minus 6, which is 12, minus, what is this? 60?
Minus 60 plus 48.
Yeah, this is also good. So we see that we are getting the same answer, which is supposed to happen because it's a property that it does not depend on what row or column that you compute the determinant this way. It has to yield the same number. So to demonstrate the strength of this,
So why in determinants always coming 0?
that is the property that it does not matter which row or column that you use. If you want a proof of that fact, that will become mathematical and irrelevant to this course. And probably I don't even remember this at the moment, just from memory.
Sir, can
Sir,
you please elaborate that? What is the meaning of determinant 0, negative, and positive, sir?
That also will
Like,
require me to explain certain things which are not part of this course. So at the end, maybe I'll take this question up if there is time.
sir,
So I think if determinant is 0, that means it has a unique solution, correct?
No, determinant is non-zero will mean that if this is the coefficient matrix, then there is a unique solution.
Oh, okay. So determinant is non-zero, there's a unique solution. And if determinant
Yes.
is 0, that means there is no solution or infinite number of solutions.
Yes, yes.
Okay.
sir, is there the row elimination principle of Gauss is in this week 2?
Yes, that will be in the next session though. Gaussian
But
elimination is one
sir,
of the last.
why one question on graded assignment 1 is based on Gauss elimination principle?
But you don't have to use
Uh,
Gauss elimination. You can just use normal evaluation of those equations.
yeah. Actually, there were two questions that we supposed to be done with determinant theory only by expanding
I
along
also
row and
found.
column. Yeah.
but yeah, graded assignment doesn't have. Great. You see, are saying graded assignment one had a Gaussian elimination question.
Yeah.
Yes, it's like Gaussian elimination question, but we can also solve with
Yeah.
row operation, like
Yeah,
expanding with
Yeah.
row.
Okay.
you can
Okay.
solve the regular equations without Gaussian elimination. I mean, I know you
Yeah,
can do it
Gaussian
with
elimination is a particular method. You can use it, not use it. Up to you. Okay. So, right. Now let's take up something else. 348, 9, let's say 0, 2.
Sir, are we summarizing the week or we just do some random questions?
I'm not doing random questions. I'm going through the content of week 2. I was just recalling what the determinant is, and there were some doubts. So I'm just
Okay, sure. Please continue.
let's just put some random numbers. So if you want to calculate the determinant of this, for example, I'm just highlighting one specific example where, you know, a smarter choice of this thing will lead to better computations. If you choose, well, in this case, you will eventually, it will be easy only. But
If we choose row
instead
2,
of doing row 1, in row 1, you'll have 3 times something minus 48 times something plus 9 times something. That 48 times something will become 0, but anyway, in this row, you will all readily see that if I take second row, for example, I'll get 0 times something. So I don't need to worry about the something because it is 0. Plus 2. In this case, this thing has a plus sign. You remember minus 1 to the 2 plus 2, which is 4, which gives it a positive sign. Times determinant of, I'll just write it as
391.
6
912.
minus,
6 minus 9.
all right. And minus, it's actually minus, but
0
minus or
only.
plus, it
Minus
doesn't
0.
matter. So
It's more
0
not
times something. So I don't need to go ahead and compute it. All that matters is this thing. I just need to do one multiplication, one addition and one multiplication.
Minus
6 minus 6. Right? So this is just some example where a particular choice of uh, row or column to compute the determinant gives you the result faster, at least from a human perspective. Yeah. And that is about how to compute determinants. And this was for now 3 cross 3 matrices. Now if I generalize to determinant of n cross n matrix, what do you expect the formula to be? Suppose I have a determinant A, whose entries are Aij. First of all, let's see what it looks like. Suppose I have A is equal to this. So this is your typical n cross n matrix, where Aij is the entry at row I, column j. Now, following the same principle, I would write determinant of A is equal to A11 times M11 with a minus 1 to the power 1 plus 1 plus A12. This is I'm expanding along the first row. A12 times M12 plus so on up until the last one. Minus 1 to the power 1 plus n, because I'm working with the last thing, A1n, M1n, right? Now, but what is M11? M11 itself is a matrix, is the determinant of a matrix which is of order n minus 1, n minus 1. Right, so if you start out with a 5 cross 5 matrix, for example, all of these things will be determinant of 4 cross 4. But how do you compute determinant of 4 cross 4? Again, you take like some particular row of that, and then you split it as a sum of terms which involve determinant of 3 cross 3. And how do you compute 3 cross 3? We have seen that it involves computing determinants of 2 cross 2 matrices. And how do you compute 2 cross 2 matrices determinant? You have to do either AD minus BC, or it is in principle doing the same thing. You take a row and do it as coefficients times determinants of 1 cross 1 matrices. So this is some sort of recursive definition where you can compute the determinant of n cross n matrices if you know the way to do determinants of n minus 1. So to do n minus 1, you go to n minus 2 and so on until you go to 1 cross 1 matrices, which is nothing but the entry itself. Determinant of a 1 cross 1 matrix, which is an entry itself. The
So
general
is 4
formula.
cross 4 or 5 cross 5 is in our syllabus?
Well, the general formula is there, but in no case you will be asked to do this.
Like
say,
the
in an exam or
Vandermandi,
something.
like things, Vandermandi, and
I am not getting what you're saying. Could you repeat that?
means like something is called Vandermandi definition of matrix. I didn't remember those things.
Even I don't remember the exact name. But in any case, this is just a general method to compute the determinant, just for your information. You will never be asked to compute even 4 cross 4 as far as I know.
I have seen 4 cross 4 once in one of the questions, but
Oh,
nothing
is it?
beyond. Yeah,
Yeah,
nothing
Okay,
there is a
right. Beyond
basic
that is,
question.
sorry.
There is a basic 4 cross 4 question there in assignments.
Okay. It's 4 cross 4 itself involves a lot of computations, and beyond that is not going to come. So in this case, you'll have a summation containing n terms corresponding to n columns. Here we are fixing the first row. So it will be terms of the form 1 minus 1 to the 1 plus j, because 1 is the row that we are working with, a1j and m1j. This is the definition of the determinant. The formula to compute it, you can call it that. And this is just for your knowledge. And then there is this notation of Cij also. This minus 1 to the power I plus j mij. This thing is called Cij, and sometimes it is written determinant of A is nothing but j going from 1 to n, ai a1j c1j. Yes. So C, M for minor, C for cofactor.
C is a cofactor, right? Okay.
cofactor of the order I, j is called Ci. It's denoted as Cij, and it is given by -1. You just put the sign as well into one factor, and then we'll get a more compact looking formula, but it's just a very minor change. And as before, the determinant need not be computed using the first row. You can do an A I naught j, C I naught j, fix an I naught, vary the j, or fix a j naught, vary the I. That also works. Let's do I from 1 to n, summation I j naught, C I j naught. So that's it about the computation part of the determinant. And then next, I think we'll look at properties of determinant. And these examples, I believe, are sufficient for the understanding of this. Otherwise, you can take it up in any of the other sessions or at the end of this session. If you still have doubts about the computation part of it, we'll take it at that time.
Oh, sir, I am talking about the companion and the permutation matrix. Sorry, sir. That time I forgot the name.
Permutation matrix.
Permutation.
Yes.
Those things are included in this week, no?
Permutation matrices are not even there in this course, no. They are not there. But permutation matrix is one specific case of a matrix, so you can compute it using this itself. It's just an example of the same. So next we'll take a look at properties of determinants. Determinant of products.
Sir, really sorry for the interruption. Can we draw any conclusion or something? Can we interpret it something geometrically by the meaning of determinants?
Yes, you can, but right now we'll not get into that because it involves something about linear independence. There is something that I can do for you in the small case of 2 cross 2. Now let us take A, B, C, D. You look at these things AC and BD, the column vectors or the row vectors, it doesn't matter. What is determinant equal to 0? That is AD minus BC is equal to 0, correct?
Yes, sir.
Now this is AD is equal to BC. Assuming that, well, you have to consider the cases when the things are 0. But for now, let us just work with A by B is equal to C by D. In the cases where B and D are 0, there will be some other things that happen that you can take care of separately. So assume B and D are not 0. So in that case, you can do this, correct? So if you do this, suppose you call it some K.
Yes, sir.
This will be A is equal to BK and C is equal to DK. So your column vectors, they were actually AC and BD. And this is actually equal to BC times K, BD times K and BD. So one column is actually the multiple of the other, correct? So if you plot these points or these vectors in the two plane, you will have BD and AC in the same line. They might be scales of each other, but they'll be along the same line. Or there is another way of saying that the area of the parallelogram. So if you have generic two vectors in a two plane, they have some area, right? There is some area.
Yes, sir. Parallelogram.
That is spanned by the area of the parallelogram for which these two vectors are the sides. That is captured by determinant. So the determinant is 0 means that over here you see that one is a multiple of the other. So, and the area is 0, correct? So area is 0 happens if and only if one is multiple of the other, correct? Or if
Yes,
one
sir.
of them is a 0 vector, which is also part of that itself. So,
And sir, what is mean by the negative?
that has to do with orientation and all that. So that I will
Okay.
not explain.
Okay, sir.
Yeah, this is relatively easier to see. It is some in some sense the signed area. So you can test out when it becomes negative area using some right hand thumb rule and
I
all that.
think when it's the negative, the orientation flips, right? Flips.
Correct. Yeah. So if you have something like 0, 1, 1, 0, which is like the negative orientation, correct? So this is just this and this, but in the reverse order. So the area of this parallelogram is 1. This is a unit square, but it
Yes,
comes
sir.
out as -1 because it is in the opposite orientation to. So anti-clockwise is generally the correct orientation or the positive orientation. So clockwise is negative. So determinant can be interpreted this way. Now in higher dimensions, like a 3 cross 3 matrix or a 4 cross 4 matrix, in 3 cross 3 you can still do a visualization in the sense that you will have 3 vectors in 3 space and then you will have a parallelepiped and the volume of that. And beyond that, you cannot interpret it, but it is still the, for an n cross n matrix, it is in Rn. If you look at these vectors, there is a volume of the solid for which these are the edges. So determinant is the volume of that. But all of this is not part of the course. This is just, it is good to see this. And when you learn about linear independence and dependence, you can compare it with this and this notion, and you'll actually have a better understanding of linear dependence. Maybe if I'm taking that week, I'll come back to this. But for now, this
Sure,
is
sure.
enough.
Sure, sir.
We
Sir.
have
Thank you
to
so much for the
increase
teaching,
freedom.
sir.
Determinant of product is equal to product of determinant. Right? So if I have two n cross n matrices, now you can work with n cross n matrices, even though you will be mostly working just with 3 cross 3, 2 cross 2 matrices. Now I can do the product of this, yeah? And determinant of the product matrix will also be a matrix of order n cross n. So that is also a square matrix. So it makes sense to talk about the determinant of that product matrix. And that will be equal to determinant of A times determinant of B. So determinant respects the product in some sense. So that is the first property. And as a corollary of this property, we have the following. So, okay, what do you know about the inverse of a matrix? Has inverse of the matrix been covered in week 1?
Yeah,
I don't
sir.
think so. No? It has?
No, sir.
Computing the
No,
inverse?
no
No,
computing
sir.
of the inverse.
No, no.
Just
No.
introduction to the inverse.
Introduction.
Okay, introduction to the inverse is there. All right. So you have, if A is an n cross n matrix, let's work with a baby case, 2 cross 2 matrix. Does there always exist a matrix such that 8B is 1, 0, 0, 1? And this is called the identity matrix of order 2, I2 or I2 cross 2. So I'm asking, does there always exist B such that AB is I?
Not necessary, sir.
No, no.
So let's take, for example, 1, 0, 0, 0. This is my A. Now, if I want a B, I'll just call this B1, B2, B3, B4. If there is something like this, then what should happen? If I do the product of this with this, I'll get B1, B2, 0, 0, correct? And this has to be equal to 1, 0, 0, 1. But this can never happen because these entries don't match, correct?
Yes, sir.
So it is not always the case that you will always find a matrix which you can multiply to get identity. Identity is like 1, the number 1. So in the case of real numbers, can you always multiply a number to get 1? Yes, as long as the number is not 0, correct?
Yes, sir.
Yeah.
If I have x, I can always do 1 minus x to get 1. But in the case of matrices, it is definitely not only the 0 matrix that does not have an inverse, but there are many more matrices. So the condition happens to be determinant of A not equal to 0 if and only if there exists B such that AB is identical. AB is equal to BA is equal to identical. So if the determinant is 0, you cannot find a matrix which you can multiply to this and get identity. This you can see using this property as well. Suppose I have determinant of A is equal to 0, then doesn't matter what I do. Determinant of AB will always be equal to determinant of A into determinant of B. And my assumption is that this is 0. So this becomes 0, correct? On the other hand, determinant of I is always 1. So this cannot be equal to this. AB cannot be equal to I because determinant of AB cannot be equal to determinant of I. If two matrices are the same, then their determinants have to be the same. But the determinant of one thing is 0 and the other thing is 1. So this can never happen. So determinant of A not equal to 0 is a necessary condition, and it is sufficient as well, that we will probably not see the proof of. But in case determinant of A is not 0, and I have, suppose B is such that AB is identity. Suppose such matrices are called invertible matrices. I don't know if this terminology is introduced, but determinant of A is not equal to 0 means it is invertible. Invertible meaning it has an inverse. It has an inverse means there exists a B such that you can multiply B to A to get identity. So if this happens, then the product rule says that this is 1, correct? Irrespective of the order of this matrix, suppose it's an n cross n, this equation is written for n cross n matrices. The determinant of identity is always equal to 1. You can expand along the first row, for example, you will get all of these things are zeros, correct? So you'll be left with only this first term. You will have 1 times minor of 1, 1. But what is minor of 1, 1? It is just identity of the order n minus 1. Once again, you'll do the same thing. This will be 1 times minor of 1, 1. And that will be an n minus 2 matrix. So you'll just do 1 times 1 times 1 and you'll just end up with a bunch of 1s. So the determinant of identity of any order is equal to 1. So is that clear? Is that part clear?
Yes.
Yes, sir. Yes, sir.
We will definitely have the determinant of the inverse of the matrix is inverse of the determinant of the matrix. So that is one way to remember. Just like we had written over here, determinant of the product is equal to product of the determinant. You can restate this thing as determinant of the inverse of a matrix. Inverse of the matrix, by inverse I mean B. And let me call this B as A inverse, just A to the power minus 1, that is called A. So that it reads better. So determinant of A inverse is 1 by determinant of A. 1 by determinant of A as a real number, it is the inverse of determinant of A, provided determinant of A is not 0. And that is happening because this is given. It is given that determinant of A is not 0, then you have this AB is equal to identity, and then B I'm calling A inverse, and determinant of A inverse is 1 by determinant of A. Or if you want to write it more fancily, you can just write it as determinant of A to the power minus 1. Now, remember that this to the power minus 1 is happening in real numbers, which means it is just 1 by determinant of A. So that's one of the properties. So in case you have to compute, let us say, the determinant of A inverse for some reason, you don't need to actually compute the inverse, which we'll see later, and then do the determinant of that. You can just compute the determinant and then you just do 1 by that. So that's property number 1. The second property that we'll be seeing is probably swapping rule. Let me just write that. Rows. And here there is no reference to rows. So rows or columns, it doesn't matter, all right? So in the context of determinant. Multiplies. By minus 1. So suppose I have the most basic example is 1001. The determinant of this is 1. Correct? This is identity. But if I swap the rows, if I'm doing the columns over here, you can do rows also, it doesn't matter. Yeah. If I make the first row the second row, the second row the first row, then it becomes this, correct? And what is the determinant of this?
Minus 1.
0 minus 1.
So this you can see very clearly over here. And if you work with examples, you can see it in other cases as well. But the general principle is that if you swap 2 rows or 2 columns, doesn't matter which one you do, there is a negative sign that is introduced. So I need another thing for that. Let me. I'm just thinking of an example where I can.
We can just swap rows to rows and columns to column.
Yes. You cannot do a row and column swap. That you can do. Row to row or column to column.
Sir, if you multiply the rows or columns with any scalars and also do swapping with to the rows or columns, so it will be any effect in the determinant by like multiplying with the scalars and
Yes,
also
that's
the
the
swapping
next
columns.
property that we'll discuss.
Okay, sure. Yes, sir.
Yeah. That's probably last property. Now,
Two swaps, and it will be neutral.
sorry.
If we'll do two swap, I mean, we have did one column swap and then one row swap, so it will be neutralized to not having any of these signs. To the
If you do even number of operations, it doesn't change this. That is the more general thing. But yeah, if you do a row swap and then a column swap, then it doesn't change. Yeah.
Sir, in your example, you have swapped both rows, right? Basically.
Yes, I've made R1 R2 and R2 R1. I cannot swap one row and not do anything to the existing thing, right? It's like I have to. Swapping means it involves two things, exchanging the positions of two things.
Okay, so you cannot just change one.
What do you mean by changing one? So let's say you have this, whatever, 7, 8, 9, let's take it. Here, this is, let's make it 7, 8, 10 just because there's a determinant 0 there, yeah? Otherwise. Now, what do you mean by swapping only one? It is, you are bringing row 1 to row 2, then what about the row 2? You have to take it to row 1, correct?
That's right. That's right.
Yeah. You cannot keep it there and just do one thing. Swapping involves interchanging the position of two things.
Yeah, two rows. Yeah, got it.
Or two columns. But if you can work out this example if you want, I'll not do it now. We're already running a little bit late. So adding constant multiples. So maybe I'll write only the rules for the rows, and for the columns it's the same. You can change the statement to columns and it doesn't matter. Constant multiples of one row, one row, where do I do this? One row to another row, doesn't change the return. Right, so suppose I have something like A, B, C, D, E, F, G, H, L, a 3x3 matrix. Now this has some determinant. You can do A times EI minus FH minus B times all that. That determinant is the same as doing, for example, here I've talked about rows, so let me do that itself. I'll keep row 1 as it is. I'll take row 1, row 2, and then I'll add some constant multiple of row 1 to this. So what have I done? To each entry in the second row, I have added a constant multiple of the corresponding elements in the first row. And let's say I keep the other thing same. So the determinant of this is equal to the determinant of this. That is what the property says. In order to understand it even better, it is probably wiser to take some example. Now, if I want to compute, let's say, the determinant of 1, 2, 2, 1, 1, say whatever, 3, 4, 6, something like this. You could go about doing it the usual way, where you expand along some row and say, let's do it along the first row. You'll get 1 times 6 minus 4 minus 2 times 12 minus 3. Once again, stop me if I'm making some computation error. This just becomes 2 minus 18 plus 10. This is minus 6, correct? So this is how I compute the determinant of this. But if I use this property, for example, I see that I can use this property somewhat cleverly, and I change this matrix to, using the property, I know that this is the same as, this determinant of the first matrix is the same as doing 1 minus 2 times 2, 2 minus 2 times 1, 2 minus 2 times 1, and the remaining things are the same. So the second and third row are unchanged. This first row, which I can call R1, I have added minus 2 times the second row to this.
So we
I've
can
taken the
subtract,
second.
we can subtract as well as add, right? Both.
Yes,
Any
add a constant multiple means the constant multiple could be negative.
negative
Right?
also.
So, yeah, it is not necessarily positive multiples. So addition and subtraction are the same. It's just a negative operation of that. So R1 minus 2 R2 if I do, I'm taking this row to, so originally my row 1 was 1, 2, 2. And I took 2 times the second row, that is 2, 1, 1. And this thing is my new first row. And that would be what? Minus 3, 0, 0. Correct? That is what I mean by doing R1 minus 2 R2. So what I'll be left with is minus 3, 0, 0. Now this is of course much easier to compute. It is just this. Minus 6, yeah, correct. So by adding constant multiples of one row to another, I have reduced the complexity of the computation. So these things are, things you should watch out for, just to do things a little bit more efficiently. And this is a property of a matrix which is pretty nice. And then the last
So
property, I believe that's the last property. Sorry, any doubt?
manipulating matrices in this level, we can aim to get more, as much as zeros in the row and columns.
Right, that is the objective typically, to use operations which, I mean, you do operations with which you can control the determinant. You do operations which either change it by only a sign or they keep it unchanged and get it to an easily computable form, and then you do the computations, minimal number of computations. In any case, you could just brute force it this way and get the answer as well. But this is just a better way of doing it, using the properties that you know.
Yes, yes, sir.
Yeah. Right. So the last property is that multiplying a row, it could be column as well. I'm just going to write row. Multiplying a row by a constant p multiplies the determinant by p. So pretty self-explanatory. So if I have TA, TB, TC, whatever D, E, F, G, H, I, and I want to compute the determinant of this, this would just be T times determinant of A, B, C, D, E, F, G, G, H, I. You can work out the proof for this. It's quite simple. We'll be doing TA times M11 plus or minus TB times M12 plus TC times M13. This is nothing but T comes out as a common thing, and then what you're left with is A times M11 minus B times M12 plus C times M13. So that's nothing but just determinant of A. That original matrix, which I'll call A, B, C, D, E, F, G, H. And now if it is not the first row, you can just do the determinant along that row, and you'll arrive at a similar expression. So proving this property is also not very hard, but I'm not going to do any more than what I've already said.
So
It's just
is
that
it
this happens.
so is it goes same with the if we multiply scalar quantity to a particular column?
Yes, because determinant can be computed along the column as well, right? So the same proof goes through. So that's what I said when I'm writing properties, I'll be saying row everywhere, but the same thing works for columns as well.
Okay, sir.
Yeah. So let's take an example. What is determinant of minus identity of order n? Anyone?
-1.
-1, sir.
-1, sir.
Okay. Let's take.
It depends.
It will depend on n, na?
Yeah, and
Order.
whether it is even or odd.
Even or odd.
What is this?
It will depend on the order of the matrix.
No, what is this? Determinant of
Be -1, sir.
-2.
1.
This is 1,
It's
sir.
1 only.
So this is not correct. It's not
Sir
true in
means
general.
it depend upon it if it is even and it is odd.
Correct. So if I have n many things, I'll have n many things, correct? Those zeros just mean everything else is 0. So I'll have a -1 to the power n.
Yeah.
So this is -1 to the power n. And you can actually say more generally, if I have determinant of TA, what is TA? TA is a matrix which is obtained by multiplying every element of A with t. What is? Can you tell me what this is in terms of the determinant of a?
T to the power
That would be t raised to the power the order of the
of the matrix.
T to the power n times determinant of a. That's
This
also
is
there.
this is only for square matrices, right?
Yeah, determinant. Whenever we are talking about determinants, it's only for square matrices. Now,
Okay.
why this t to the power determinant of a? If I have some, let's say a11, a1n, I'm not going to write everything, and up to ann. Right? This is your typical n cross n matrix. Now, if I multiply every element by a factor of t, it is the same as multiplying the first row by t, the second row by t. So what does this property tell you? The property tells you that multiplying a row by a constant t multiplies a determinant by t. Now I'm not multiplying only one row, I'm multiplying each row. So for each row, I get one t in the determinant, right? So there are n rows, so I get n t's multiplied together, which gives me the t to the power n factor outside. So this property actually implies that determinant of TA is t to the power n determinant of A. So this is a trap sometimes that we just look at determinant of minus I and think it is -1, but it very much depends on the order. More generally, when you're multiplying a whole matrix by something, there are n rows, right? So there will be n t's which come outside. So you'll get a t to the power n as the factor outside. Something to keep in mind. And that's all about determinants, I believe, for now. Let's go to Cramer's rule.
Sir, if we are asked to compute the inverse, we'll simply put 1 by determinant A, right?
That is determinant of the inverse. That is not the inverse. The inverse of a matrix is a matrix, correct?
Right. So that
So how do you
computation.
compute the determinant? Sorry, the inverse, we'll get there.
Okay.
Yeah.
So you'll be sharing this note, right?
Yes, this will be posted in that. There must be a folder shared with you, right?
Excel sheet, yes.
Yeah.
Okay.
So you'll find all the notes there.
Okay, thank you.
Yeah, so remember that our initial objective was to study things like ax equal to b or ax equal to 0, which is a system of equations typically in n variables, m equations in n variables where m and n need not be equal. But for the specific case that m is equal to n, that is if you have a square matrix as the coefficient matrix. So, and the determinant is equal to, not equal to 0. Right? Determinant not equal to 0 is a special case as we have seen. Determinant not equal to 0 ensures the existence of an inverse, and it is in some sense
Invertible.
yeah, it's invertible. So for at least that specific case, how do we compute the solution of the system of equations for which the coefficient matrix is A? So that is given by Cramer's rule. This is one of the rules which you can use. So when to use is coefficient matrix is square and invertible. Well, invertible means it is square. So I'm just going to write it, but it's mildly redundant. Coefficient matrix is square and invertible, then you can use Cramer's rule. Now, how to use? Right? Make new matrices. So let's say, yeah, I'll give you the general thing and I'll give you an example that probably make it clear. Construct matrices AXI. I think this is the notation in the Prof's notes. Just go take a look at it and verify. If it is something else, just use that thing. I'm just going to call it AXI. Just give me one moment. Yeah. All right. Let's continue. So we construct these matrices AXI by replacing ith column by constant vector B. Then xi is equal to determinant of AXI divided by determinant of B. Now, this is a little too formulaic, so let's do it with an example, then come back to this. Suppose I'm given a system of equations. Let's call it 2x plus 3y is equal to 10 and 3x minus y is equal to 4. I don't even know what the solutions are, but can I apply Cramer's rule to get the solution of this? So there is one fact which is maybe, I don't know if it's discussed or not. If you have an invertible square matrix as your coefficient matrix, then the solution is unique. And that unique solution is given by this form. And with an example, it will be clear. So in this case, what is the coefficient matrix?
2, 3, 3 and minus 1.
Right. And what is the determinant of the coefficient matrix?
Minus 11.
Minus 11.
Yeah. So what are the conditions that you need to verify to determine whether or not you can use Cramer's
Determinant
rule?
of A is not equal to 0.
Yeah, which in this case it is, right? It is not 0. So the criteria that need to be satisfied to the Cramer's rule are satisfied. Coefficient matrix is a square matrix which is invertible. Invertible meaning determinant not equal to 0. You don't need to explicitly find the inverse, that will come next. But as long as determinant is not equal to 0, then we call it invertible. In this case, it is. It is a square matrix. It is invertible because determinant is minus 11. Now, what is AX1? So let me just write this in the standard form. Correct? So this matrix is the coefficient matrix. This is the variable vector, or I don't know what it is exactly called, but this is the constant vector. Right? This is like AX equal to B. So how do I construct AX1? I look at this matrix A. I replace the first column. So AX1 only does something to the first column. So the second column remains the same. But what is the first column? I replace it with the constant vector.
Minus 4.
Correct?
Yes.
And then I do determinant of AX1. What is determinant of AX1?
Minus
10 minus
52. Minus 52.
Minus 22.
Minus 22.
This time we are getting nice matrices. So that's good. So what about AX2? AX2 is you are going to change second column, that column number 2. So the first column will remain as the same as A, but the second column will be replaced by the constant vector being this. So what is determinant of?
Minus 24.
22.
22.
Minus 22.
Oh, sorry. Minus 22.
Yeah, minus 22. So now X is determinant of AX1 divided by determinant of A and y is determinant of ax2 divided by determinant of a. We have used x and y and x1 and x2 and be consistent with it, but it's just some notational stuff. But anyway, what is determinant of ax1? Minus 22 and minus 11. So you have a minus 22 divided by a minus 11, and y is also minus 22 divided by minus 11. This is 2 and this is 2. So the solution to this thing is 2, 2. 2, 2 is the unique solution. To the given equation, to the given system of equations. Right, let's just verify that. If I do 2 into 2, 4, 4 plus 3 into 2, 6, that is 10, and 3 times 2 minus 2 is 4. And for 2 plus 2, probably it is of comparable difficulty to just solve it. For 3 cross 3, you can look at examples in 3 cross 3 as well. In 3 cross 3, what are you going to do? You are going to get ax1, ax2, and ax3, which are obtained by replacing column 1, column 2, column 3 by the constant vector b, and those three, and you'll get an x, y, z, which is given by determinant of ax1 divided by determinant of a, determinant of ax2 divided by determinant of a, and determinant of ax3 divided by determinant of a. So that's all about Cramer's rule.
Sir,
So, yeah.
if I'm not wrong, the reason for replacing the constant matrix, constant matrix with the column of the coefficient matrix is that the each column in the coefficient matrix replace a one particular variable.
I am not sure why, as in the proof of this, I don't remember, and the proof will probably definitely shed a light on why replacing something by this works. There is also, okay, I'm not sure about that. I'm not sure about
So,
why this works the way it works, but this is
sir,
the method to do it. Yeah.
we have to do in the same way for 3 by 3 matrix.
Yes, you'll in the case of, wait, let me answer the other question first. So
Yes.
I don't know why this exactly works at the moment.
Okay.
But
Yeah.
sir, logic behind to
But it
replacing
can be
this.
one of the valid logic, right?
It could be, but the proof will say
Yeah,
whether
it
it is
can be
actually
different.
correct or not. But I'm not sure. There is another way to look at it. There is a three blue one brown video which talks about Cramer's rule. It is very nice. You can take a look at it. I don't have the link right now.
Can you
Yes,
say
sir.
the name again?
There's a YouTuber called three blue one brown.
Three blue, one.
Sir, from the playlist Essence of Linear Algebra, right? It's from the
I
playlist
don't
Essence of Linear Algebra.
I don't know what playlist it belongs to, but I've seen that video at some point. But it does make use of transformations and all that. So it is still good to take a look at it to understand why such a thing works.
Sir, can you
But I don't
share the
remember
link
right.
of that video, sir?
Later I'll do it. Right now I'll just go ahead and finish the.
Three blue, one brown.
All his videos are nice, but there is one in particular for Cramer's rule. If you are interested in this week, because since you have the thing ready. Anyway, let's continue. And I'm not going to do a 3 cross 3 example. The 3 cross 3 example works absolutely similarly. First, you look at the 3 cross 3 matrix, compute its determinant. If it is 0, you cannot use Cramer's rule. If it is non-zero, then you can use it. Well, if it is 0, you cannot use the rule is evident because of this determinant coming in the denominator, right? So, of course, this formula will not work in that case. So once you have the determinant, then you construct three matrices, one obtained each by replacing the ith column by the constant vector, and then you compute the corresponding determinants, and then you take these ratios to get. So the ith altered matrix, by ith altered matrix I mean replacing column I by the constant vector. The ith variable matrix, the determinant of the ith variable matrix divided by determinant of A will give you the value of the ith variable in general. If it is an n cross n matrix, you will have n of these ratios corresponding to the n variables that you have to find. I'm not going to do a 3 cross 3 example unless someone explicitly wants it. Does anyone want an explicit example of a 3 cross 3 matrix
No, sir.
solving?
No, sir, it
It
is
is
fine.
only for
No,
us.
sir, it's fine.
Sir, we have to solve the same way just we have done before this.
Cramer should be only for square matrix.
Yes.
Yes.
One more question. Is Cramer's will Cramer's rule every time it would give unique solution or it would change?
It is a unique solution because determinant is non-zero. If you have a non-zero determinant square matrix, the system always has a unique solution.
Sir,
Yeah.
in
So
the
why
same
can't
way,
it have infinite or no solution?
Sorry, could you repeat your question?
Why
sir
can't
for
Cramer's
3 by
One at a time, please. Aditya, maybe first. Hello.
sir for 3 by 3 matrix we have to solve in the same way.
Yes, you have to replace each column by the constant vector, just like this. You'll get three matrices, and you'll have your original matrix. So you'll have determinant of ax1 by determinant A, determinant of ax2 by determinant A, determinant of ax3 by determinant A, which will give you the values of the three variables.
Excuse
What was
me.
the other doubt?
Yeah.
Yeah.
Why can't we use Cramer's rule to find for infinitely many solutions or no solution? By
As
using
soon as you have the determinant to be invertible, the determinant to be non-zero, meaning the square matrix is invertible, then it forces it to have a unique solution.
Yes, sir. But how to find infinitely many solution or no solution?
That is comes when Gaussian elimination that we'll see in the second session.
Okay, so
The
thank you.
most general method is Gaussian elimination, and see the Cramer's rule again is one of those things which is part of the syllabus. You need to learn it, how to do it, and all that. But to compute the unique solution, you can use any of the methods. Like even when the determinant is non-zero, there is just computing the inverse and finding it, which I'm going to discuss now as the last part of this session. You can use this or Cramer's rule or Gaussian elimination. Gaussian elimination works for anything. It does not require it to be square matrix or invertible. And invertible is an even more particular case. So it works even for rectangular matrices. So the Gaussian elimination is going to work for everything. But for invertible square matrix coefficient matrix, then for these there are these methods also, which may be in some cases simpler. Shall I go ahead?
Yes, sir.
So the last topic for this session is inverse of a matrix. We discussed some things, some important things about inverse of a matrix already. Let's complete that discussion. So as I was saying earlier, A is said to be invertible if there exists B such that AB is equal to BA is equal to identity. Identity of the appropriate order. So here this could be n cross n. Then you need to have B to be n cross n itself. And this is identity of order n. Correct? Now, one we have seen is that in this case also B will be denoted by A inverse for obvious reasons. What we have seen is A need not always be inverted. which means, does there exist a B? Not always. But suppose you know that such a B exists, correct? Is such a B unique? If it exists.
Yes, it would be unique.
Can you tell me why?
Because there would be inverse of the determinant. I mean, 1 by determinant for the like cofactor what we are finding.
That all comes after knowing how to compute the inverse. But if I'm telling you how to compute the inverse, it is implicit in that statement that it is unique, which is not immediate, or which is not something that we know already.
We can prove it by uniqueness theorem given in the lectures.
Yeah. That is what. Do you remember the argument for that? Let's look at, suppose B1 and B2 are inverses of A. Suppose I can have more. Then I'll have that AB1 is identity. This is because B1 is an inverse of A. Now, if I multiply this by B2, I can do this, correct? I can multiply by a matrix on both sides and the values will still be the same. Now, associativity of matrix multiplication will tell me that B2 into identity, any matrix into identity is just that matrix. That is why it's called identity, correct? But what is B2A? B2 is also an inverse. So B2A is also identity. But identity times B1 is again B1. So B1 has to be equal to B2. Is this clear?
Can you please say one more time how P2
Sir, yeah,
P2
please
is
explain the part B2A. Yeah, B2A is equal to identity. Why it is?
Because we have assumed that there are two inverses. So what does, suppose B1 and B2 are inverses of A, what does it mean? It means that B1A is
okay, you
equal to
just assume
AB1.
P2 is inverse.
Okay, sir.
B2A is also satisfying the same condition. Right?
Yes, I also.
Yeah, so it's just some pre-multiplication by the same matrix to get that B1 is equal to B2. So you cannot have two inverses. If there is an inverse, which need not be the case always, it is unique. Now, the question is how to compute the inverse of a matrix. Once again, why this method actually works is not something that I'm remembering the proof of, but I'll tell you the methodology. Let's work with an example first so that it doesn't become too technical. Let's do 1 to 1, 3, 1 to, I don't even know if this will be a good matrix. Maybe the computations will be ugly, but let's go with it anyway. Something. As long as the determinant is not 0, I'm fine. So to compute the inverse, so the objective now is to compute the inverse. How to compute the inverse? Okay. As we were discussing earlier, if the determinant is 0, then it cannot have an inverse that we have seen. So first you compute the determinant of this. The determinant of this is what? 4 times 4 minus
Should be 7, sir.
1. Oh, thanks.
1 minus 6. Yeah.
Right. 12 minus 5. That's 7. Correct. Thanks.
7, 7. Yeah.
So this is the determinant is equal to this. So the inverse of this we can compute. There is no obstruction of the determinant for the existence of the inverse. And yeah, another side statement is that we have seen that if determinant is 0, then inverse cannot exist. But we have not said that if determinant is non-zero, the inverse exists. That is something that I'm just going to state. And now I'm going to tell you how to compute the determinant.
So in the conditions you have described in previous, just above, sir. Here you are assuming those conditions, no?
Which one?
This one, the second one. B2A into B1. You are assuming this condition.
The question that I'm trying to answer is this. If a inverse exists, is it unique? So typically to show that something is unique, what do? You say, suppose it is not. Suppose there are two things which satisfy this condition. Then you have to conclude that they are the same. Is that fine? So this argument shows that inverse is unique. Are you convinced about that? Are you convinced about the logical flow of that argument?
No, at first you are saying that B1 equal to A1 B equal to identity matrix. It's okay.
Yes.
But the second condition, B2A equal to A B2 equal to I. In this place, you are assuming two conditions in the same way.
Yes, I am saying that suppose there are two matrices which are inverses of A. Right, B1 and B2 both are inverses. What is an inverse? An inverse satisfies these conditions. So B1 is also an
nothing
inverse.
but
B2.
I by A. Suppose A is a matrix.
Yeah, it is not right to call it I by A because there is no division of matrices.
Correct.
Or 1 by A, we can say.
No, it is not 1 by A. It is a matrix which, when multiplied to the given matrix, gives you identity. So, I mean, for your understanding, you could call it something like 1 by A, but that is not correct because of non-existence of division.
Sir, I didn't understand the last part, sir. Like the conclusion.
Okay, so if I have, so all of these steps, did you understand?
Yes, sir. The conclusion, that is B1 equals to B2. So what's that? Like, yeah.
B1 is equal to B2. The argument is fine, right? To get B1 equal to B2.
So could you please explain one more time, sir?
Yeah, actually it's simple. Yeah.
So the thing is, whenever you have to show some property is satisfied by only one thing. So you have any property P satisfied by only one object A. So you assume the negation of that. You assume that it is not true. Suppose it is not true. Suppose that there are two things which satisfy property A, and then you use a sequence of logical statements to arrive at the fact that those two things are the same. So if there are two things which satisfy the same property and they are equal, then it means that there is only one thing that satisfies the property. Correct?
Yes, sir. Here, like as here, B1 is equal to B2 means there will be only one unique matrix which will be satisfies AB is equal to Y.
Yeah. You if you understand it, it's fine. But there are people who seem to have not got this thing. So let's see if everyone is on the same page. Is that fine? The others?
Yes, sir. It's fine now, but this example is getting quite confusing.
Yes, and now it's fine.
This example is not completed yet. I have not computed the inverse.
No, why you taken the 401 in the last row?
It's just some matrix I took so that we can just work with anything. You can work with anything. I can give you the general formulas given by MIJ,
Why you taking the 401? I understand.
It just took determinant by taking third row.
For the simplification of the data, we had
It's
possible.
easier. Zero is there, right?
It is
Yeah.
easier way. Yeah.
I could even do this also, but yeah, let's not go that simple. But let's leave it there. Anyway,
Let's continue.
where were we? So this, even if you don't understand this part clearly right now, it's okay, because this thing is like, the proofs of things are not important as far as the objectives of the course go. It is okay at a basic level if you remember that inverse is unique. This is sufficient for you. You spend some time after the session and try to look at this and try to understand what I've said. If you don't, then ask me in the next session. I'll revisit this. All right.
Yes, sir.
Okay, sir.
Okay. Yeah. So, right. Computing the inverse. Computing the inverse can be done once again only when determinant is non-zero. So first you compute the determinant. Now in this case it is non-zero. It comes out to be 7. So we can go ahead with the computation of the inverse. Now what we are going to do is compute the cofactor matrix. I think it is called cofactor matrix.
Yes, it's cofactor.
The cofactor matrix of an n cross n matrix is also an n cross n matrix. In this case, this is a 3 cross 3 matrix. Now I have to compute the corresponding cofactor matrix. Now, how do I do it? It does involve something similar to, oh yeah, why it is obviously called cofactor matrix, because the ijth entry of this is Cij. If you remember Cij, what was Cij? Cij
Minus
is
1
minus 1 to
of
the
ij
power I plus j mij.
MIG.
to m of I.
Right. So it is the signed determinant of the minor of Ij. So this is called the cofactor matrix. So in this case, let us do it step by step. If I have, for this matrix, I want to compute C11. So for C11, I look at this matrix, like I remove the highlighted row and column, and what I'm left with is 1, 2, 0, 1, right? So I have only 1. The determinant of that is 1 minus 0, which is 1. So just for clarity, I'll write this as C11 is minus 1 to the power 1 plus 1, 1 into 1 minus 2 into 0. Correct? This is the definition of Cij. And minus 1 to the power 1 plus 1 is just plus 1. And this is 1 minus 0, which is 1. So for the second entry, what am I going to do? I'm going to look at this matrix. It becomes 3 minus 6. The M12 is 3 minus 8.
3 minus 8.
Is minus 5.
Minus 5.
But here it will become plus 5, because the sign is minus 1 to the power 1 plus 2, which is minus 1. There's a minus sign that comes along with, strictly speaking, it is minus of minus 5, which is 5, which is, let us keep it as minus of minus 5 just for clarity. Right? And for A33, we'll look at this and you'll get minus 4. And what about the next one? Now I'm not going to shade everything. So if you look at 2, 3, you will have the minor as 2101. If you are not following what I'm saying, stop. Okay, so for the next entry, I need minus of, because this comes with a negative sign, minus of 2 into 1 minus 0 into 1, which is just, next thing is a plus, which is the determinant of 1141, right, which is minus 3. Next one is a minus, which is 1240, which is minus 8. And then Next one is a plus again, which is 4 minus 1, 3. Next one is a minus again, which is 2 minus 3, which is minus 1. So let me write as minus of minus 1. And the last entry is 1 minus 6, which is minus 5. So the cofactor matrix is nothing but the matrix of cofactors, which are sine times minors. Is that clear? Is it clear how this matrix was obtained?
Yes, sir. Yes.
Yes, sir. Yes, sir.
So next you have what is known as adjugate.
So the power of -1 in the cofactor matrix would be depended upon which thing?
I plus A.
Power of what?
E and J.
So if you're looking at the ijth entry of the cofactor matrix, it comes with the sign -1 to the I plus j.
Oh, okay, sir.
Yes, yes. Actually, cofactor minus 1 power by I plus A only.
Sorry. This is just cofactor
It's
matrix.
transpose
This
of
is cofactor matrix. I don't know if it is called COF of A or C of A probably. Whatever is in the notes, please follow that. I might not be using the precise terminology, but it's just a transpose of it. So rows become columns and columns become rows. So this thing is 1, 5, minus 4. This is the first row of the cofactor matrix, becomes the first column. The second row of the cofactor matrix becomes the second column. And the third row of the cofactor matrix becomes the third column. Right? And then inverse of it
1 by determinant.
is 1 by determinant of A times
Adjoint of A.
adjugate of A.
That is just
1 by 7, right? Yeah. All right. So this is the inverse of it. Just to verify in this one case, let us do the computations. It will not be very pretty, but let's go
Sir,
1,
in
2,
the
1, 3, 1,
adjugate
2 whole
matrix,
zero.
sir, in
Just
the
a moment.
adjugate matrix, it would be minus sign for 5.
1, 2.
Sir, one
So in
thing.
the
Sir, one thing.
adjugate matrix,
Sir, is it called adjugate or adjoint? Can we call it adjoint also?
adjoint
I
matrix.
believe it's called adjugate.
In a different, like in LCRD, it's given adjoint. That's why he's asking.
Okay. Okay.
Yes, sir.
Let
Yes,
us
sir. I
follow
am also
the
confusing.
terminology of the lecture videos. And I think there it is called adjugate.
Okay.
So that will be
The
the reference point
adjugate,
for us
the adjugate is nothing but changing the row and columns
of the
by changing
cofactor
sign.
matrix. Not by changing the signs. Like, so here 1, 2, 3 was a column. Here, sorry, 1 minus 2, 3. It becomes the rows. The rows become columns, the columns become rows. You're not doing anything to the signs.
Transpose of cofactor.
So here we are multiplying with a cofactor.
See, cofactor is already multiplied. It's like minor multiplied with the appropriate sign being -1 to the I plus j. That is your ijth cofactor. Put all the ijth cofactors into a matrix, it becomes a cofactor matrix. Take the transpose of that, it becomes an adjugate matrix. Transpose just means make the rows the columns, make the columns the rows. Or take the mirror image of that across the diagonal if you want to look at it like that. So you get the adjugate and then multiply the adjugate by the reciprocal of the determinant or the inverse of the determinant, then you get the inverse.
Sir, but why you here minus or minus 5? Why you written here in the first
Just to
row?
emphasize the fact that this thing is a -1 times, so it is -1 times the minor, which is -5.
The condition is saying to do that.
So C
Yes, it's
1, 2
so
is
definition.
-1 to the power 1 plus 2 m1 plus m1 2. Sorry. which
Yes, sir.
is
M12.
minus of M12, and M12 is minus 5. Okay, so this is 5 because it is minus of minus. I'm just writing minus of minus 5 to make it clear that minor is actually minus 5, and then you have to multiply by the appropriate sign, which is a minus, which gives you a plus 5.
So, sir, the components of the above diagonal and below diagonals will be changed only.
Yes, the diagonal remains the same,
Hmm.
and you're taking a mirror image across the diagonal.
Hmm. Those components will be changed only.
Yes. So, for example, these two are changed. These two are changed. Like here it was 1 and 8. That has become 8 and 1 over here. Similar things have happened. So you can look at transpose that way also.
Yeah, basically Aij is equal to Aji.
Yeah, Aij. I mean the transpose A tilde Ij is Aj. This is the definition of the transpose. Since
Excuse me, you have just missed something. In the inverse thing, you just missed a sign over there. A33. That's a minus 5.
A33 is a minus 5. Yeah, thanks. Thanks for pointing that out. And let us do this matrix multiplication. 5 minus 3, 1, minus 4, 8, minus 5. The 1 by 7 will keep it outside and do this matrix multiplication. If not all of the entries, okay, let's try to do all of the entries. It's 1 plus 10 minus 4, which is
Minus
11
4.
minus 4, 7.
7.
Next you have minus 2 minus 6, which is minus 8 plus 8, 0. Then you have 3 plus 2, 5 minus 5, 0. Next you have 3 plus 5, 8 minus 8, 0. Minus 6 minus 3 minus 9 plus 16. Right? Yeah. What is minus 9 plus
Excuse
16?
me, sir. Here I
That's
know
7.
what is happening.
7.
You can verify that this happens. So
7.
let us verify that this happens. 9, 10, 10, yes. 4, 0, minus 4, yes. Minus 8, 0, 8, yes. 12, 0, minus 5, yes. So now that we have a 7 outside, we can just multiply this to just 1, 1, 0, 0. So in this case, we have verified that this actually gave the inverse, but in general, this is the method that works. So what do? You first compute cofactor matrix. So how do you compute cofactor matrix? The ijth entry of that would be this, and then you do adjugate matrix. How do you do that? You take the transpose of the cofactor matrix. So this is actually just Cji, which is minus 1 to the I plus j m j, and then divide by determinant. Compute inverse.
By determinant of original matrix, right? The main matrix.
Yes. I'll just call this Aij inverse, but this is not okay. That's actually confusing notation. Let me just call it Bij or something. That would be Aij divided by determinant of A. The original once again Aij is not. Let me just call something Bij or something. So the component of the ijth component of the inverse of a matrix is minus 1 to the power I plus j mji divided by determinant of A. And that is sort of a convoluted way of remembering it. The easier way to remember it is in these steps. Compute the cofactor, compute its transpose, divide by the determinant. That's much easier to understand, but yeah, this is the formula. And you can verify that you can look at a proof anywhere that this actually works for any matrix for which the determinant is non-zero. As soon as the determinant is non-zero, you can compute what is known as the inverse. And we have seen that the inverse is unique. Now come to the solution of a system of equations Ax equal to b. Once again, so whatever we do using determinants or whatever, our end goal in some sense is to analyze the system of equations. Understanding the system of equations is our objective, right? So once again, if I have, just as in Cramer's rule, if A is an invertible square matrix, once again, square is kind of redundant. So what you can do is, this is an equation of multiplication of matrices, correct? I can multiply this by A inverse. Now I know that there is a unique A inverse in this case. What would happen to A inverse Ax? This would be equal to A inverse B. Because Ax equal to B, I am multiplying by this matrix A inverse, which I know how to compute. And then I use associativity of the multiplication to get A inverse A. X is A inverse B.
So we know that A inverse A is the identity matrix.
Yes, so X is forced to be A inverse B. Now, you recall the fact that inverse is unique. So this A inverse is a unique matrix. So that specific matrix times the constant vector is the only possible solution, because so these conditions force that X has to be A inverse B. So now you know why in the case the coefficient matrix is a square invertible matrix, the solution is unique and it is given by A inverse B. So going back to this example where we used Cramer's rule, right? Let's try to compute the same thing, 2x, 3y, 10, 3x minus y, 4. Let's do that using this method. 2x plus 3y is equal to 10. We already know the solution to this, but let's do it again. 3x minus y is equal to 4. So in this case, what was A? 2, 3.
2, 3, 3 minus 1.
Correct? Now what is conjugate of A, which I'll denote by C of A? Just check if that is the notation. So the first thing comes with a plus, minus 1. Just minus 1 is
Minus
remaining.
1.
The second one is a minus 3.
Minus 3.
The third one is also a minus 3.
Minus 3.
And the last
2.
one is a 2.
2.
Right, so this is the conjugate. Oh, first of all, determinant, I think we had already computed there. You need to verify that this is okay. This is non-zero. By okay, I mean it is non-zero. C of A is this. What is adjugate of A?
1 minus 3. It will be the same. So
Yeah, this is a
it will be the
symmetric
same.
matrix. So
Mhm.
the adjugate, the transpose, and I mean the adjugate and the cofactor matrix are the same. Now, what is A inverse then?
Adjoint 1.
Minus 11.
Correct?
Yes, sir.
So A inverse we have computed. Now we were
Minus
trying to solve the system Ax equal to B. I know that Ax
Mhm.
equal to B has the unique solution. In this case, you have an invertible square matrix. So X is equal to A inverse B is the only solution. That's what we said over here, correct?
Yes, sir.
So let's try to compute X is what is X is equal to A inverse, which is 1 by 11 of 133 minus 2 times
Multiply by
what was B? 10 4.
10 4.
There's a 1 by 11 outside. But what about the rest? You have a 10 plus 12, which is a 22.
22.
And then you have a 30 minus 8, which is also 22. You get a 2 code. So this is the unique solution. So you can either compute the inverse of the coefficient matrix and multiply it to the constant vector to get the unique solution, or you can use Cramer's rule. So what we have seen in this session, to summarize, after the properties of the determinants and how to compute determinants and all that, we have analyzed only the special case where the coefficient matrix is an invertible square matrix. And these are two methods, Cramer's rule, where you have to replace columns by the constant vector and compute certain determinants, or you compute the inverse of the matrix and just multiply it to the constant vector to get your solution. So yeah, two ways to find.
So sir, to find out the adjugate of a matrix, we have to delete the ith row and jth column.
It's the same as cofactor. It's just cofactor. How do you compute cofactor? You do -1 to the I plus j times determinant of the submatrix formed by deleting the ith row jth column. Same thing.
The cofactor of this A, can you explain? I'm quite confused.
But it's I'm a bit confused on how to find the adjugate.
Oh, adjugate is just transpose. Okay. If I have, let's say A, B, C, D, this is your, call this matrix M. What is M transpose? So here AB is a row. See, one way to see is that you take these rows, AB and CD are rows, right? You make them columns. This is called a transpose of a matrix.
Or we can say, we can
or
change.
you look at the diagonal and interchange the symmetric things. Like in this case, there's only one change that you have to do.
Mirror
but
image.
If you had, yeah, but if you had, let us say, 2, 3, 1, 1, 0, 1, just for an example, this is a rectangular matrix. This also has a transpose. Transpose is not something that is for square matrices. So in this case, though, you don't have a diagonal, you don't have a mirror image. You just have rows become columns and columns become rows. So this is it.
So if I told you to find out the determinant of this matrix, then?
No, determinant is only for square matrices. Transpose can be done for any matrix, but determinant is only for square matrix. Is that okay?
Can I explain this cofactor of -1, -3?
This specific example, is it?
Yes.
Yeah. In this case, what is the first element of the cofactor matrix? C11. This has to be -1 to the power 1 plus 1, M11, correct? Now, what is M11? M11 is obtained by deleting the row containing 1, 1 element, the row and columns, row and column which contains 1, 1. So what is remaining is just -1, right?
Yeah.
So this is just -1. So the -1 to the 1 plus 1 is +1, and M11 is -1. What is C12? -1 to the power 1 plus 2, which is 3, times M12. Now what is M12? I remove this and this. I am left with only 3. Typically, for bigger matrices, when you do such remove the row and column, what you're left with is a submatrix. And you have to compute the determinant of that. In this case, that submatrix is a 1 cross 1 matrix. So the determinant of that is just that itself. So it's I. So this is nothing but -3.
Okay.
C21 is -1 to the power 2 plus 1, M21. Now M21 is again 3. So this is also -3. And C22 is -1 to the power 2 plus 2, which is 4, times M22. If you look at M22, the only entry that remains after you remove the second row and second column is the 1 entry, which is 2. So this is just 2. So you have 1, -3, 2.
Okay, okay, I'm very clear. Thank you, Mister.
Sorry?
Yeah, thanks.
Yeah, okay.
Okay.
And that's where we'll stop. So yeah, computing the inverse, using the inverse to compute the unique solution of a certain type of system of equations
Sir,
using
for
Cramer's rule.
third order matrix, how can I
Yes,
find out the adjoint? The same
the
process.
same way. Yes. What about this was specific to 2 cross 2? There was nothing like that, right? See, the cofactor is a point by point you do it. So computing the minor you can do for 3 cross 3, computing the cofactors you can do for 3 cross 3, 4 cross 4, n cross n, anything you want. And then you put all the cofactors together, you get a cofactor matrix. Taking the transpose, you can do for any order matrix. Multiplying by a constant, you can do for any order matrix. Even though here I have only showed you the case for 3 cross 3. In fact, over here we did for 3 cross 3, right? 3 cross 3 and 2 cross 2, we did explicit examples, but the principle is the same. Is that fine?
Yes, sir. Yes, sir. So we can also find the inverse, like converting the identity matrix and converting the A matrix into the identity matrix by applying the same row operation on the identity matrix and A
Yes,
row.
you can do that, but I don't think that's part of this course. As in, you take A and I and do row operations on this to make this I,
Yes, sir.
and whatever comes over here is A inverse. That is another
Mhm.
method, but I don't know if it is any easier or harder than this. So,
Sir.
Yes, sir.
Suppose you write a matrix, third order matrix. Now
any
I am
third order
saying.
matrix?
Suppose first row is 1, 3, 2.
Yeah.
Second is 2, 0, 4. And third is 3, 6, 5.
Okay. Yeah.
I find the adjugates.
So at what point, as in, what is your mental block? Where are you stuck? Because I have explained the thing, right? So how to compute the cofactor. I can do the same thing for this matrix, but I want to know what your source of confusion is.
Sir, here we have to take the reference of 1.
There is no reference of 1. So for the cofactor of, let's call this matrix M, cofactor of M, let's compute C23. Okay. The rest of the things you can compute in the same way. I'll just tell you what C23 is. There's no reference to 1. There's no reference to anything. These are some entries which you can compute. I'm just going to tell you how to do C23. This is -1 to the power 2 plus 3 M23, which is -1 to the power 2 plus 3 is a negative number minus determinant of, for M23, you look at the thing which remains after you do this. This is 1336. This is -6 minus 9, just 3. Is that fine?
Yes, sir. Now it's fine.
So
Okay.
this is 3. And similarly, you do for every other entry. All right.
Yes, sir.
Okay, then. It's about time to stop, unless there's some doubts.
Sir, this PDF is available right now or by tomorrow?
I'll be uploading it tomorrow probably. I can upload it right now. I have to go though. I'll do it tomorrow. Is that should be fine, right?
Yes, sir. If you upload now, it's done.
Okay.